With the terminology and common user expectations for foldable devices firmly under our belt, let's start modeling and extracting this information so we can build our app to adapt to these devices. If this is your first time here, welcome to my channel. Every week, I give you seasoned advice on how to build professional Android apps in bite-sized chunks. Now, let's start writing some code. Like our previous effort with non-foldable devices, let's begin by modeling what data we'll receive. Here is a quick overview of what we can get. First, we can get the hinge position. That is, describing where the hinge divides the screen, whether horizontally or vertically. Next, we have a derived number that I call the hinge separation ratio. This value isn't explicitly provided to us by the Android APIs, but it's something that can be calculated from the previous value to tell us whether the hinge goes straight down the center, as it does on most phones, or is slightly off-center. This isn't likely to be very helpful right now for applications running in full screen mode, as most phones evenly divide the screen straight down the center. But as manufacturers experiment with new form factors, this will allow us to compensate for hinges that may not evenly divide the screen into two equal parts. It also will allow us to build applications that allow split screen mode or floating window mode. We may find the hinge separation ratio to be helpful whenever the user has moved the application slightly off center so that the hinge no longer goes straight down the center of the screen as it would if the application were in full screen mode. Next, we can get whether the hinge is separating. This is provided by the OS to tell us whether these two screens should be considered visually separate based on the hardware build. And finally, we have the occlusion type. This value is also provided by the OS to tell us whether a visually occluding hinge divides the screen into two parts, or if there is a flexible screen to join the two parts to appear as one continuous display. With that in mind, let's build a model to hold this information for us. In Android Studio, I'm going to open up the screen classifier interface again, and let's add another sealed interface inside of it called half opened. This interface will model the foldable devices with the single hinge that are partially folded. It should inherit from the screen classifier interface just like the fully open data class does. Inside of it, I'll add four properties: hinge position of type rect, hinge separation ratio as a float, is separating as a boolean, and the occlusion type of type folding feature.occlusion type. Right now, this is a generic representation of some kind of foldable phone. Now we can become more specific. I'll create a data class inside of the half-opened interface called book mode to model devices held in the book mode posture. It'll inherit from the half-opened interface and will be responsible for overriding all of the abstract values from the interface. I'll create one more data class right below called tabletop mode for the opposite posture. Once again, it'll inherit from the same interface and override the same values. That's all we need to do to model our data. Let's start extracting it. I'll need access to a library called Window Manager. In my app's Gradle file, I'll add a reference to that library and synchronize. The next part of the project continues in the main activity. I'll use the window info tracker to extract information about the current window and save its output into a variable called device posture. Since this function uses Kotlin flows, I'll have to provide a default value using the stateIn function. I'll bind this flow to the lifecycle scope, start it eagerly, and provide an empty initial value. Notice how all of this was written outside the set content block, unlike our previous work. I'll pass the information we just obtained to the multimodal composable. Once inside of the composable, I'll transform the state flow into a state like this. Note that anytime the flowable updates the state, it will trigger a recomposition. Therefore, we will always be sure to have the latest information reflected in our app thanks to this behavior. Finally, I'll pass this value as another parameter to my createClassifier function. From here, we can transform this data into the model we created just a moment ago. Since this function is no longer focusing solely on reading the size of a flat screen, I'll move its current behavior to a standalone function called createFullyOpenedDevice and pass it the window DP size. We'll use the space inside of the createClassifier function to make a few high-level decisions for us. First, I'll need to know if this device is a folding screen. I can get that information by asking the window layout info object if it has a folding feature. I can do that like this. I'll call devicePosture.displayFeatures.find, and I'll look to see if any of those features is a folding feature. Then I'll cast the outcome of that operation and save it as a variable. This variable will be null on standard phones and tablets, as well as on foldable devices when the screen is either fully open or if it's folded shut and the user is simply using the outer, smaller display, like on a Samsung Galaxy Z Fold device. Next, I'll create a few helper functions to help me determine if the device is in book mode or tabletop mode. The first function I'll create is called isBookMode, and I'll provide the folding feature device as a parameter. From here, we can check if the device is half opened and if the orientation is vertical. If these checks pass, the phone is in book mode. On a similar note, let's create the isTabletopMode function. Nothing here should surprise you. Once again, I'll check for the half-open state and if the orientation is horizontal. Let's go back to the top function and start using these new functions. At this point, I'll double-check to ensure the createClassifier is returning a screenClassifier type, that is, the root sealed interface of our data model. Since we're now dealing with a more generic class of devices, this function must be able to model and transform all of these types. Under the folding feature variable, I'll create an if-else chain. First, if the folding feature is null, that means we're not doing anything special with the foldable device, so we can return the result of createFullyOpenedDevice. Next, I'll check if we're in book mode. If so, we'll return the result of a new function I'll call createBookModeObject, with the folding feature as its only parameter. This function will return screenClassifier.halfOpened.bookMode. We'll populate that function in a moment. Next, I'll check for tabletop mode and create a similar function for that transformation operation. Here, it'll return screenClassifier.halfOpened.tabletopMode. Finally, we need a catch-all scenario, which I'll simply consider to be a non-foldable device. I'll be sure to return the values of each function. Now we can turn our attention to modeling the book mode posture. Most of these properties are simple to map. The hinge position comes straight from the bounds property of the folding feature. IsSeparating and occlusion type are mapped the same way. I'll need to manually calculate the hinge separation ratio. I can do that by determining the window width by adding both the left and right bounds of the hinge together. Then I can get the left side of the hinge and divide it by the total window width. Notice how everything is converted to a float, since the only possible values for this operation will lie between 0 and 1. In most scenarios, that value will be 0.5 for hinges that separate the screen straight down the middle and when the application is operating in full screen mode. If the hinge were slightly to the left of center, that number would decrease. If the hinge were slightly to the right, it would increase. Finally, I'll use that property to set the hinge separation ratio. That's all we need for this function. The tabletop mode posture will be very similar. However, instead of calculating the hinge from left to right, I'll do the same math using the top and bottom values instead. Now, we've modeled and extracted just about everything the Android APIs can tell us about foldable screens. Well, let's start to use these values. We already have all of this information being sent straight to the screen info view, so now we can just start using this information. For the bottom 3 text and spacer composables, I'll surround it with an if check. I want these values to show up on foldable devices when they're being folded, so I can check if the screen classifier is of type screenClassifier.halfOpened. Inside of the if statement body, I'll keep the first text value the same. However, I'll display the hinges data inside of the second one. I have a string resource already available to help us out. That resource is called hinge position coordinates. It takes 4 parameters for the top, bottom, left, and right bounds respectively. Down in the last text composable, I'll display the hinges width and height. Again, I have a string all ready to go for this purpose. It's called hinge position size, and it takes the width and height as the 2 parameters. Everything is ready for our app to start reporting the data it receives from the hinge. Let's try it out on a real device. Going to the screen information view, you can see the output looks similar to how it did before we added foldable support. However, once I begin to fold the hinge, the UI suddenly changes. The data is showing us that the hinge is running from top to bottom and is in book mode posture. Rotating the device shows similar information, but in tabletop mode posture instead. At this point, our app is smart, but not incredibly exciting or very useful. It's time to turn our attention toward building an interface that can adapt this information and really start to leverage the advantages of each form factor. We'll begin that work in the next video.